Welcome back to our new class. The last class we have seen the various deformations which is happening. So here basically we have seen the elastic and plastic deformation, and we have just seen the names of two common mechanisms which is occurring in the plastic deformation, that is slip and tuning. Today we will see the details and the difference between these two mechanisms. To starting with, first we will focus on the slip. Okay, so slip, there's a history behind the slip. Actually, in the slip we can see the external deformations like this. Okay, external in the sense the deformation for the body, a plastic deformation for the body we can see. But when scientists have taken the X-ray diffraction, okay, X-ray diffraction details we will see in the next class, but for the time being just understand that it is a technique which is used to study or to view the crystal structures. Okay, and they have taken the extra diffraction with the intention that there is some crystal structure change happen to this location, but what they have seen is that they haven't changed any crystal structural change. That means external shape has changed, but internal crystal structure has not disturbed. So scientists started working on it, and they came up with a model known as slip model. Okay, where the unit cell or the atoms slip over one another, producing a macroscopic shape change without having a crystal structure change. Okay, and the condition is that it occurs on the planes having the greatest density of the atom. Okay, the last class we have seen what is the atomic density, various densities and all. So the planes which have the most number of atoms or the highest density, okay, in that areas, on that planes, the slip actually occurs. Okay, or in other words we can say that along the closest packed direction or in the closest packed planes. Okay, so we will call this direction along which the sliding happens, okay, along which the crystals or the atoms or the unit cell slides, is known as the slip direction. Okay, this is one thing. Initially it was here, and what will happen is that this will move to the next place or next lattice. These three atoms will move to the next atoms. So this happens, this continues, this will result in a slip. Okay, so in more detail we can see, you can use these kinds of figures for your exam purpose. Okay, under the influence of a shear force, when a shear force is given as shown in the figure, okay, initially the atoms A, B located in between CD and DE. Let's see this figure. Under the influence of a shear force, atoms move relative to each other on certain plane. Okay, certain planes, not in all planes. Please stress this word, under certain planes, from one position of equilibrium to another. This will cause a permanent deformation. Okay, when a shear force is applied like this, what will happen is that it will just move, this layer will just move. This will cause a deformation. This cannot be identified with the help of XRD, X-ray diffraction. Can be a macroscopic change. Okay, because the edges will look like something like ruptured. Okay, so the slip actually occurs on a certain plane which is known as slip plane. And the direction which we have studied is known as the slip direction. And the combination of this crystallographic plane along which slip occurs and the crystallographic direction along which these atoms moves, the combined system is known as a slip system. Okay, let's see this figure. This is the crystal edge or the surface, let's say the surface, not the crystal surface, it's our macroscopic structure before the deformation, and after the slip it will look like this. You can see some slip bands. Okay, so these are the planes with along which the slip occurs. So these colored this colored area are known as slip planes. Okay, when some shear stress acts, and if we take some photographs, it will look like this. Okay, you can it have a similarity to that of a weld surface. It will look like this, which indicates that a slip has happened to that particular location. Okay, and that particular thing, that this particular width, small width, is known as a slip step. Okay, so please be careful this one. And okay, now let us see the thing, like mechanism. It occurs actually in the 4-stage mechanism. This is the stage 1. Okay, in stage 1, this is a regular crystal. Okay, when a force, a shear force, when it is applied, what will happen is that it will start deforming, and at the highest density planes, okay, let us consider this as the slip plane. Okay, and this will move along this slip direction. What is that? This is the slip plane corresponding to that figure, and what will happen is that this section, the full set of unit cell will move. Okay, and at the edge we will get a step. Okay, this is known as the slip step. Okay, so I think everyone to everyone that is clear. And now let us see, this is the slip which occurs throughout here. This will be the mechanism. You can see the animation of the slip, and it has a representation of, or what to say, that this slip movement, we can say it is analogous to the movement employed by a caterpillar. I think everyone knows this caterpillar and how it moves. So you can I don't think there is much need for this explanation. From the figure itself you can understand how this thing is moving. This is a actually this move. Also, what will happen is when the force is applied, it will move from one portion to another. Actually, not the atoms are not this atoms will move to this location, creating a vacant space here, and finally this vacant space is moving until it reaches here. So this particular portion is known as the slip band. Okay, so it is analogous to the movement of a caterpillar. Just see the animation. Okay, so now some commonly observed slip systems in metals. You can see that this is the commonly occurring slip systems. In FCC, it is the slip plane and slip directions are given is 111 and 110. Along this slip plane and along this slip direction, most of the slip happens. Similarly, for BCC and HCP, you can see the slip plane and the slip direction. So in general, slip systems to look like this. When a shear force is applied like this will move, and it has a wave-like nature like this. It will move until it reaches the end, creating a slip edge or a slip band. Okay, now let us see an important law which is related to this slip. Okay, it is known as the Schmidts Law. Okay, it is also known as Schmidts factor, okay, which describe the slip plane and the slip direction of a stressed material, okay, or we can say how much amount of shear stress is required. What is the minimum amount of shear stress required to initiate a slip? Okay, so it's a very interesting theoretical portion. Okay, the Schmidts law. Let us first see what do you mean by a Schmidts law. Okay, the Schmidts law. Uh, the Schmidts law states that there is a stress which is known as a critically resolved stress. Okay, we will see in the next slide what is critically resolved stress, shear stress. For the time being, just understand this one. Tau r is equal to the stress applied on the material. So it's the stress applied. We can say that tau r, which is equal to the stress applied on the material, that is sigma, multiplied by the cosine of the angle with the vector normal to the glide plane. Okay, or we can say that it's as a glide or a slip plane or a sliding plane. We can say whatever it is. So this is the slide plane which we focus here, and there is a it is acting along, or the axis is in this way. So we can see that this is the normal to the slip plane. This is the normal to the slip plane, and this is the slip direction along the slip plane. And this angle, this particular angle, is known as beta. Okay, so it is the let's come to the law again. It's equal to the stress applied on the material multiplied by the cosine of the angle with the vector normal to the glide plane. So it will be like cos beta again multiplied by cosine of the angle with the glide direction. Okay, so this is the cosine of the angle, this angle what they are mentioning. This is along this direction, slip direction, so it is alpha. So what he mentioned is that Schmidt mentioned is that the critically resolved stress tau r will be like sigma into cos beta into cos alpha. So this is known as Schmidt's law. So now we will see the derivation in the next slide. And coming to the critically resolved shear stress, we can say that it is a component of the shear stress resolved in the direction of the slip, which is necessary to initiate the slip in a grain. That is we can say that it is a stress, shear stress, which is achieved so as to start or initiate the shear stress or initiate the slip in a particular crystal system. So this is the derivation, and we can see that Schmidt's law, a shear force Fr is there, Fr along this direction, and we have seen alpha and beta in the earlier slide. So this is the force applied, this is the slip plane, and this is our cross-sectional area, that is A, and we can see that this is slip plane, and when it is acted, so we can say that this angle will be beta. Okay, since this is alpha, we can say that this angle will be beta, and we can see the area of the plane, or A naught. We can say that this A naught will be, if we resolve it to here, we will get A naught is equal to A cos beta, or in other terms we can say the area of the slip plane is equal to A naught by cos beta. Okay, please keep this one in mind. And next thing we want to find is the shear force, that is Fr, shear force or the force along the slip plane. Okay, we know this is the applied force, that is F, or the applied stress is F by A naught, and F is the applied force, and when it resolved along the slip direction, that is resolved to this one, it will be Fr, or Fr will be F cos alpha. Okay, so shear force is we have found out, this part we have completed, and area of the slip plane also we have completed. Now we want to see the resolved shear stress. Okay, resolved shear stress tau r is defined as Fr by A. Okay, Fr by A, which is equal to F cos alpha by A. A is A naught by cos beta. So cos beta, and on solving this equation we will get F cos alpha cos beta by A naught. But this F by A naught, this time, okay, F by A naught, we know it is the applied shear stress, this one. So it is taken as F sigma cos alpha cos beta. This is the Schmidts, this is known as the Schmidts law. Okay, here we have one more thing, like whenever the resolved shear stress, that means whenever this factor, whenever this resolved shear stress reaches a critically resolved shear stress value, okay, whenever it reaches a critical value, that is tau r, whenever reaches a critical value, here the slip begins. That is the condition. Okay, so now let us see the next deformation, that is the deformation by twinning. Okay, here in certain materials, when shear stress is applied, the plane of atom in the lattice move parallel to a specific plane. Okay, so that the lattice is divided into two symmetrical parts which are differently oriented. Because if we take, okay, if we take some XRD for this one, we can see that the crystal structure have a different orientation. Okay, so this phenomena is known as twinning. Okay, so there is a twinning plane, the plane parallel to which the atomic movement, the total dislocation happened. Okay, so the twinning region, we can say it as a differently oriented region in the within the crystal and the twinning place. This zone or this particular region is known as twinning region, and there's a direction along which the twinning happens is known as twinning direction. So twinning is most common in HCP crystals, because it's also seen in FCC and VCC, but it is very rare. It's common phenomena in hexagonal close packed crystal structures. Okay, during twinning, the lattice over the twinned region may get favorably oriented for slip with respect to the applied load. It can lead to the this slip, or it can regions may get favorably oriented for the slip, because after twinning it can just follow to, it can move to a slip. Okay, so this is a figure which clearly indicates the difference between two mechanisms. This is our original crystal, and when slip occurs it will look like this, but when twinning happens it will look like this. Okay, twinning entirely different type of crystals, because all the crystal structures have dislocated. Okay, but the surface deformation is not that much as that of the slip. So this is purely on examination point of view. Many times you can expect such kind of questions, like explain the difference between the slip and the twin. So just you can follow this table. Okay, I will explain one on each part. This is the slip. Regarding slip, involves a sliding movement. Okay, this involves a sliding movement. Okay, this involves a sliding movement of atom on the slip plane. So here the slip plane is very important. Okay, atoms, it will move only in this slip planes. But twinning involves displacement movement of atom relative to each other on many planes, because here the planes are not specified. It can occur in any plane or in any direction. But slip, it won't be like that. It will occur only on a certain plane. Now, next one is the orientation of the crystals above and below the slip plane before and after the slip is same. Okay, that means the crystal structure we have seen earlier slide, that the crystal structure won't change, or in other terms, it cannot be identified with the help of a XRD. But here it is entirely different. Okay, the crystal twinning plane, the oriented sides have different structures, and it will be like a mirror image, okay, of the original lattice. Now, next thing is the atomic moments are of one or more atomic space. Okay, here the atomic moments are a fraction of a atomic space. Through microscope, slip appears as thin lines. Just we can see it as a thin, small lines. Okay, small lines. But here it appears as a broad line. To look like a broad lines. The microscope. Okay, that these things we will see in the next slide. More clear images we can see in the next slide. The slip is initiated even at lower stresses. Okay, at small stress, only thing is that there's a particular stress known as critical stress. At that stress, the slip will be initiated. But twinning occurs at higher stresses. So this is the thing which we need to take care. Minimum value of the stress is called a critical shear stress, is required for the slip to take place. For twinning, there is no such stress or no such thing. It will occur at some higher stresses. It can be at any point. It can be at any within. If the stress is very high range, it can occur at any time. So the observed in all types of crystal lattice slip, it can be seen in HCP, it can be seen in FCC, it can be seen in BCC, or whatever it is. It can be seen in every crystal lattice. But here it is most common in HCP crystals only. Okay, but it will happen in FCC and BCC, but it is very rare. But it is most common in HCP crystals. Steps formed by slip are visible only on the surface. Okay, if the steps are removed by polishing, no evidence remain. Okay, that slip steps, if we just grind it, or if we just machine it, we will not see it. But here, since there is a difference in the lattice orientation occur in twinning, even if we remove the surface steps, because inside we can see the markings. That means with inside also we can see that difference in the crystal structures. Okay. Now here the slip line may be present in even or odd numbers. Okay. So here the twin lines here always occurs in pairs. Okay. So on the last slide we have seen that the slip lines is very thin. Okay, here you can see the very thin, but here it is like a thick bands we can see. This is how we can identify it through a microscope. Okay, so that's all about the slip and twin. And one more topic we need to discuss. This is the dislocation density. Okay, dislocation density is the measure of number of dislocation in a unit volume of a crystalline material. First, there are two methods to measure this one. First one is the total length of dislocation line in a unit volume is measured. This is used one technique. We what we will if I let me take the pen. Okay, if a crystal structure is like there, and many dislocations are there, and the line we will take a line, and the total length of the line is measured in a unit volume. Consider this as a unit volume, and in that volume the total length of that line is measured, and that length by the volume will give the dislocation density. Or in second method is used here, instead of volume we will use the area. Okay, here what we will do is that there is a this is a area, and we can see many number of dislocations are there. We will calculate, or we will count the number of dislocation, that is 1 2 3 4 5. So 5 dislocations divided by the total area of that particular portion. Okay, that will give the dislocation density. The second one is most commonly used technique. So with this dislocation density, we can find the strength of these structures and the applications in which it can be used. So that's all for this video. In this video, just winding up, we have just seen the two basic mechanisms in which the plastic deformations occur in the crystals, that is the slip and the twinning. And we also seen the Schmidts law, which tells at what particular stress this slip will start. And finally we have seen the dislocation density. And in the next video we will see the production of X-rays and how XRD is used for evaluation of various crystalline structures. Thank you for the attention.